right, before I start talking about antimatter physics, antimatter rockets, going to other stars, traveling interstellar, I think it's important that we ask ourselves a question, and that is why explore space? You know, we have so many problems here on Earth. You know, we have global warming, hunger, war. Why should we spend time, spend money, and effort going into space when we could be spending that time and effort here on Earth? You know, I could list all of the technological advances, the medical breakthroughs of over 4 decades of human space travel and space, but I think the real question is why explore? You know, I think simply the answer is it's in our DNA. We are the descendants of people who were curious and who explored their environment, and I think we need to continue doing that. But there's a problem. There's a big problem, and that is that rockets are too slow. In order to demonstrate that, our fastest object that humans have ever created is the Voyager 1 spacecraft, and that moves at 15 kilometers a second. Now, that may seem like a fast speed, but if you want to go to Mars with that speed, it would take months to get there. If you wanted to go to Pluto, which NASA just did, and they spent $1 billion in 10 years to get there, it just takes too long. And the final example is really the most important one, is that if we want to get to another star, our closest star system, Alpha Centauri, as you see there, is about 4 light years away, and that's 38 million kilometers. So it'll take about 30,000 years at 15 kilometers a second to get there. And you know, I don't want to wait around for that. So luckily, human beings are actually quite good at developing tools that allow us to explore our environment. In the 1700s, we built very accurate measurements of time. We built the chronometer that allow us to travel the seas and allowed for really the golden age of exploration. In the 1900s, the Wright brothers developed flight and allowed us to master the skies. Now, if you really want to explore beyond our solar system, we're going to have to come up with a new tool. You know, being an antimatter physicist, I'm kind of partial to antimatter, but it could be something else. It could be laser propulsion. It could be laser fusion or solar cells. Some physicists even think that we can bend space-time and travel faster than light. But I think antimatter is actually the nearest term and most realistic. So, a little bit about antimatter. It was first predicted by Paul Dirac up there in the top right corner. You know, he was actually struggling with 2 relatively new concepts, one being special relativity, which describes really life at really high speeds and the speed of light, and quantum mechanics, which describes the Earth or the world of the very small, atoms and molecules. So he's solving this relativistic quantum mechanics equation. He came out with 2 answers, a positive energy and a negative energy for these particles. You know, how many times have you been doing your homework and you come up with a negative answer and you just say, oh, let's throw that away. We'll just look at the positive energy solutions, because that's what it makes sense. But Paul Dirac was a genius in that he saw these negative energy solutions and he said, wait a minute, maybe there's a whole new set of particles out there that we haven't even seen. So some people thought he was crazy, of course, but it was only 3 years later that Carl Anderson at Caltech saw this in his cloud chamber. He saw the track of a particle going, curving, and it had the same energy and mass as an electron, but it was actually curving the wrong way. It should have been curving to the right if it was an electron. So this is actually the first experimental evidence of antimatter, or an anti-electron, which we like to call positrons. So antimatter I like to describe as mirror matter. So if there was an anti-you in a mirror, it would look exactly like you, except everything would be flipped. And the same is true at the subatomic level. Anti-electrons have the same mass as an electron, just positive charge rather than negative charge. And that's why we call them positrons. So, an interesting characteristic of antimatter is annihilation. It's quite unique in that if you have an antimatter particle and a matter particle and they get close enough together, they'll both disappear and turn into pure energy. Now, this is the universe's most efficient means of turning mass into energy. And it's actually quite powerful, and that's actually what got me interested in positron physics years ago. What does that mean in terms of energy density if you had a clump of antimatter? Well, antimatter has about 90 megajoules per microgram. I know that doesn't mean much to you, but to put that in more familiar terms, if you had a gram of antimatter or an M&M-sized piece of antimatter, it'd have the same amount of energy as about 80 kilotons of nuclear weapon. Or alternatively, about 10 million liters of liquid natural gas, about a full tanker load. So, not only does antimatter have incredible promises as a fuel for spacecraft, but this has some pretty significant applications in the future of energy research, energy production, especially in inertial confinement systems and pulsed energy delivery. But I'm more interested in the propulsion side of things, and so is my company. The original concept of antimatter propulsion, it was actually developed in the 50s by Eugene Sanger. And what he did was he said, what if you had a clump of antimatter, you took it out in your spacecraft, and then you annihilated it in the rocket engine nozzle, and you're able to direct that energy flow. You're able to direct those gamma rays so that you have thrust in one direction. This was cutting edge at the time, but there were really three problems, one of which was production. You can't create enough antimatter to do this, unfortunately. The other is that you can't trap the antimatter. Of course, that property of annihilation, which is good for the energy density, is actually really bad for being able to trap it. So you need very high-strength magnetic fields, and it just wasn't feasible. It still isn't feasible to trap large amounts of antimatter. The third problem with the original concept was directing that energy. Gamma rays are much higher energy than X-rays. And of course, if you go through the TSA and in the airport, they X-ray your bag. X-rays tend to go through everything, and gamma rays even more so. So reflecting gamma rays is something that we can't do right now. So I started thinking about these problems in 2011, finishing up my PhD in positron physics, and I realized that the real issue, the limiting factor, was when you went from hot positrons to cold positrons. Now, state of the art in 2011, you had your source of hot positrons. And what they did, or what they still do, really, is to run it through a solid piece of material. Now, what this does is it's very thin, so that most of the positrons just travel right through. A very small number will actually stop inside the material. And of course, a large number of those will hit an electron, because our matter is made of a lot of electrons, and you'll lose it. A very small number, about 1 out of 1,000, will actually make it to the surface and be emitted as a cold positron. So you have to be able to create cold positrons in order to work with them. They come out 1 million times hotter than the surface of the sun, so you have to be able to cool them down. This process was very inefficient, so we started thinking of new ways to do this. My lab partner and I discussed this over about a year, came up with a napkin sketch of an array moderator. Soon after that, we made it an actual patent. And then actually we asked for some money from a grant, and we were funded by the Thiel Foundation to do the initial proof of concept on that moderator. So this moderator now forms the heart of all of our propulsion concepts, and that little piece up there is actually very tiny. It's about 3 by 3 millimeters, but it's the source for all of our antimatter concepts. So when you're developing a concept, you also have to develop a team. So back in 2012, asked some friends of mine who I was working on another rocket project there in the desert with, said, well, let's give up this chemical stuff. Why don't you guys come help me build an antimatter rocket? Who's going to say no to that? So we rented a little office, brought in a bunch of nuclear science equipment, quickly realized that the landlord didn't appreciate that. So we got kicked out of there. And the next year, we moved into a little more appropriate facility. And then last year, finally, we made our way down to a nuclear fallout shelter with a clean room. And so this new facility will allow us to develop some of our concepts and integrate them into a CubeSat, which is a very small satellite. Very easy to launch, very easy to demonstrate new concepts on. So how do we get around those three issues? Production, trapping, and directing the energy. Well, the first two issues of production and trapping you really get around by having a very efficient moderator. Now, we use a radioisotope source of positrons, which continuously emits positrons. We run it through our little tiny moderator, and we can create a very high-intensity positron beam. Now, the third challenge of directing the annihilation energy. Now, in order to do that, we transfer the kinetic energy of the gamma ray into a charged particle via fusion reactions. And now we have a charged particle that's high energy rather than a gamma ray. And that's important because charged particles like to follow magnetic field lines, as you know, from the aurora borealis. So we use magnets like the one in the bottom right there to actually direct the energy and produce thrust. So in about 2 years, we were hoping to put a demonstrator CubeSat, that little tiny spacecraft, into orbit. So why is this useful? What is a really small spacecraft going to do for you? Well, it turns out about 4 billion people on the surface of the Earth don't have access to internet. So there's a lot of companies that want to launch constellations of small satellites into low Earth orbit. And what that will do, they'll create a global network of broadband internet so that anyone can access that information. I think that would be an incredible opening door for the Earth. A little bit further down the road, what we want to do and what government agencies want to do, and some private companies like SpaceX, they want to send things out to Mars. And our technology would allow them to do that and cut the transit time significantly. And then kind of a far out application for this is asteroid mining. I know you've probably never heard of asteroid mining, but it turns out a very small asteroid in our asteroid belt, metal rich, is worth a lot of money. And with chemical rockets, you can't just go out there and get it. You need something like an antimatter system. So in terms of extending this technology into human space travel, that will require, of course, a lot of work. It turns out that our squishy bodies can only really handle about 1 g of acceleration. And even so, 1 g, 9.8 meters per second, is actually a pretty high acceleration. NASA took 10 years to get to Pluto. If we go at 1 g, we can get there in about 3.5 weeks, which isn't that bad. If we want to go to Alpha Centauri, the story gets a little different, and we start bringing in concepts of special relativity. Now, if we want to go out there at 4.3 light years at 1 g, it'll take about 5 years, going about 85% the speed of light. Now, once we start getting towards a significant fraction of the speed of light, we start getting time dilation, which is an interesting phenomenon, but really it's the thing that allows us to travel out into the universe. So while 5 years has elapsed on the spacecraft, and only 9 years has elapsed on the Earth, which it's getting weird, but still feasible. If we extend this out to Kepler 452b. Now, Kepler 452b is an interesting place because a lot of people call it Earth 2.0. It's a little bit bigger than Earth. It's in the habitable zone of its sun. So it's actually, a lot of people want to go there and see, well, maybe there's life, and I think there's a good chance that there might be. Although it is 1,500 light years away, with our 1 g spacecraft, we could get there in 12 years on the spacecraft. Unfortunately, 1,500 years will have passed on Earth. So things are getting a little weirder. Now, if we look at the ultimate application of this, exploring to the edges of our universe, 13.5 billion light years away. At 1 g, we could make it there in a human lifetime, 30 years. Now, we're going incredibly fast towards the speed of light, but the only problem is that 13.5 billion years would have passed here on Earth. So what I'm trying to say is that with a transformative technology like this, we have to think seriously about the consequences and actually new questions that arise. The first of which is if we want to really explore beyond our solar system into our galaxy, we're going to have to do it ourselves. If we do send a probe or a robot, we'll never hear back from it, essentially. And then the second issue is that if we do want to go out into beyond our galaxy, we're going to essentially be saying goodbye to this. And, human beings used to be a nomadic species. So one of the questions I am asking you is that, do we want to become nomads again? Thank you very much.